we are going to be looking at probability. This, you see, one of the things about data science is the same as business analytics. The only thing is that data science is more in mathematics and computer science department. That's the name they use. But when it comes to business schools, we don't want to call it data science because it's more business applied. So we call it business analytics. But they are both using the same tools, mathematics and statistics. Mostly these two are what, and then we use the computer to actually do the coding and programming. Now, one of the fundamentals of data science or business analytics is probability. That's what we want to look at today. So my goal is basically to help you to be able to explain the basic concept of probability. Okay. We'll use Venn diagram to do a few things. Okay, who can tell me what Venn diagram is basically about? What do we normally use when we are dealing with Venn diagram? What do we use? One word. What do we use when we are dealing with Venn diagram? Raise your hand and tell me. When you are dealing with Venn diagram, what do you normally use? We use what, Stella?
Sets.
Set. And we also use something. Apart from sets, we also use something. You can tell me. The moment the word Venn diagram comes to your mind, there's something we use in drawing. There's something we use in the process of drawing. What is it that we use when we are drawing? Or you guys didn't do secondary school? Yes, Gloria. Gloria.
Yes, sir. Please, we use a box and two circles.
Exactly, circles. Basically, circles. That's what we use. Okay? So we use that to be able to understand some few things. Guys, I beg you, to be able to focus and understand, you need to pay attention. Sometimes it's not that the thing is hard, it's because your mind itself is divided somewhere. If right now you are driving, you will not concentrate. If right now you are among some people, you will not concentrate. But if right now you have a table, you are sitting in front of a table, you have a laptop with you, and you have a book and you have a pen, I promise you, and there's nobody around you, you will concentrate. You will eat the content beautifully of what we're about to do. So always have that in mind. Okay, the word probability, give me a synonym for that. Give me a synonym for probability without checking it anywhere. Okay, just on top of your head, what is another synonym, Saibu?
Say likelihood.
Likelihood. What other word, Emmanuel?
Chance.
Chance. What other word? Stella. Steven.
So I was about to say chance also.
Okay, Steven.
Possibility.
Possibility. Very good. Okay, guys, please remember that I like those who are commenting, because when you comment, that is when I am more likely to give you a free topic and then work with you more. So if you know that you will ever want to work with me, let me know you. Communicate more. Talk more here. That's the only way I'll get to know you. All right. Now, possibility. So probability deals with chance. Probability deals with something that is not there. It's not exact. It is estimated. It's not there, but it is an expectation that it will be there. Okay. Okay. So it's a likelihood of an event happening. That is sometimes the main definition for probability. The likelihood of an event occurring. Now, the event can be a random experiment, a process that leads to an uncertain outcome. For example, if I throw a coin, we'll be using the coin power. So please, if you don't have a coin, I have a coin here. If you don't have a coin, get a coin. It helps you to understand. Normally, the original coin used to have a head and a tail. These days, there are several things, and now those head coins are. But normal coin is head, a tail, head, a tail, head, a tail. We're using a coin. Have that in mind. We'll also be using a Ludo dice. I hope you know a Ludo dice. That one, I don't have it here to show you. random experiment is something you do where you don't even know what is going to happen. For example, sometimes two football teams are going to play football. And you say that what is going to be the score? You're only predicting. You don't know the outcome. And anything where you can't predict what's going to happen is a random experiment. The outcome of the random experiment is what we call the basic outcome. And the experiment could be done multiple times. For example, I can throw the coin once, twice, 3 times, 4 times. That creates what is known as a sample space, where it is made up of several outcomes of the random experiment. So the first one you throw, you get a head. Second one you throw, you get a head. Third one you throw, you get a tail. Next one you throw, you get a head. In that circumstance, those head, tail, head, those ones are called outcomes. And when you put all of them together, it is known as the sample space. What are the 3 things you should know? Random, uncertain, outcome, the result, sample, the number of the results. These are the things you should write down as part of your note, because as we build up your vocabulary, you see that they get plenty. Now, what is the event? The event itself is that outcome from the space. So any subset of the outcome from the space, that is an event. We'll look at a number of examples here. So I want you to look at this set here, okay? And if you look at this set, you have a set A and a set B. They have been shaded in such a way that the set A itself, okay, and when I say set A, I'm talking about the entire space A plus the A intersection B. I remember last year when I was doing this, somebody says, A, you AB. So let's assume that you have 2 events. See, the event can be you studying right now with me, or you cooking. These are 2 events. And the thing is that you may not be able to do both at the same time. But sometimes too, you may be able to do both at the same time. Now, if event where you are learning and the event where you are cooking, these are 2 events and they are all in the sample space. Then we can say that the intersection of learning and cooking at the same time is going to be the outcome that belongs to both the A and the B. That is, it belongs to both cooking and learning at the same time. So there are some situations where you cook. There are some people, they are cooking, they will never be part of this learning. They have turned on their thing, but they are not learning. And there are others that will be learning alone and not cooking, but some will do both, learning and cooking at the same time. That is the A and B. That is the A intersection B. This is called events that is an intersection event, or event of an intersection. But there's another event which is known as mutually exclusive event. You see, if the 2 events are mutually exclusive, what does that mean? It means that doing one will not allow you to do the other. Guys, understand this mutually exclusive event because you will need it a lot when it comes to Bayesian theory. Mutually exclusive events are 2 events that do not have anything in common. So you decide that you are not going to cook at all, purely learning. But he decides that he's not going to even log into the Zoom at all, purely cooking. So there is nothing like doing both in these 2 situations. And therefore, the intersection between the A and B, that is doing cooking and learning at the same time, is an empty set. How do you think the graph will look like? The drawing of such an event. If a circle represents the event and another circle represents the event B, what do you think it will look like compared to the previous one? How would it look like? Stella.
So they wouldn't meet. They'll be two separate.
Exactly. There will be two separate circles. Okay. And that is exactly what you see in this context. So you should be able to distinguish a mutually exclusive event and an intersection event. Now, what do you think can be another name for the intersection event? Based on what we've just discussed about mutually exclusive event, what would be another name for an intersection event? Joshua?
Mutually inclusive.
No? I know you're going to say that. It's still around there. Ebenezer?
A union.
No. But in fact, this one, you can even find a union here. Amina?
Say inclusive.
No, he said inclusive and I said no. See, I can drop B into A, it's still inclusive. Drop B, so I can just go and look at A alone, okay? Just have A alone and then drop B here. If I drop B, B is still inside A, so that's still inclusive. But if you remember the one that we did, part of it was inside A, part of it was outside of A, so that it can be inclusive. Okay. There's a name, it's just like the same name as you see, but just something small change. George?
I think it's a joint event.
It's a joint event. That's another name. It's a joint event. But there is a better name. Because the joint part is the intersection part. Abigail?
So I was thinking maybe a mutual event.
Well, it's a non-mutually exclusive event.
Okay.
It's a non-mutually exclusive event. A joint event, it is. So just note the difference. So if you don't know that this previous one was a non-mutually exclusive event, it is. Okay. Now, another person also mentioned a union event. Okay. Now, the union event, you're not separating them. Okay. And I'm going to ask you about that very soon. So if A and B are two events, the union of A and B is a set of all possible outcomes in that set. So everything in A and B is a union. Now, what do you think happens here when it comes to the intersection? Is there an intersection? It's an intersection, but then we don't take care of what? We don't consider the intersection. Who can tell me why we don't consider the intersection? Because the union already takes care of the intersection. Okay. So you can see that we have not technically included A intersection B here. Remember that because the union, it does not look at A intersection B, but looks at A union B, okay, and it doesn't include the intersection. If you want to ever include the intersection, you've got to redefine it. I'll come to that. It's very important you get that part of it. But the key point about the union is that you have A, all the elements of A, and all the elements of B without considering an intersection part. Okay. So let's take an event. Event 1, event 2, event 3, all the way up to event K. All of these events are said to be collectively exhaustive events. Another word, collectively exhaustive. What does that mean? It means that event 1, union event 2, union event 3, all the way up to union event 3, that make up the set. So when you come here, which part are we talking about? We are talking about everything here plus the space outside the colored region. That's the white space. The white space. So when we talk about collectively exhaustive, we are talking about the white space as well. The white space, white space as well. So they make up a sample set. If anything is not in the circle, the collectively exhaustive will only include a circle. In other words, A union B will be equal to the collectively exhaustive set, provided there is no event outside of the A union B. if provided there's no event outside the A union B, then the collectively exhaustive event make up the A union B. And if you don't understand, please ask. The next thing is complement of an event. An event called event A has a complement if there is something that doesn't belong to A. Okay, so let's go back here. I was going to draw, but let's go back here. In fact, let me just use this one. Because I was just going to. So if you take, for example, here, okay, what is a complement of A here? If you look at, you have to describe, by the way, what is a complement of A? If I were to kind of label them nicely, okay, so this is A, this is A intersection B. I'm just renaming them. Then the other part is B. What is A complement here? Who can explain? You have to explain. What is A complement? Remember, we said that a complement of an event is anything that is not part of the event. So here, what is a complement of A? Ima?
It's B.
Yeah, that is what somebody would have said. Stella?
So I'm thinking B and anything else outside the circle.
And what is that?
The S. Oh,
Exactly. The white space.
The white space.
So it is not just B, but it's B and anything outside the A, which is the white space. So a complement of A is an important terminology that you should be able to understand. Valentine.
Sir, please, I want to ask that if we are trying to describe this exclusively mutually exclusive events and the collectively exhaustive events, can we use the words universal sets to describe the S? Since it's the bigger set, and then we have
yes, you can use the universal set. You can.
Okay, sir.
Yes.
Thank you.
All right, so let's continue by looking at a typical example of a sample space. Whenever you throw a dice, guys, when you throw a dice, the dice is made up of 6 sides. 6 sides. The entire sample space is 6 numbers, each representing a side of rolling the die. My question, and there are several questions you can ask when it comes to this. If we let A be an event, where this event is the number rolled is even number. So if A is an even number out of the sample space of 1 to 6, and if B is an event representing number rolled is at least 4. And please focus on me, don't look anywhere. Okay. So if I roll, the number rolled is 4. That is event B. And the first one is number rolled is an even number. What will be the answer for event A? Number rolled is an even number. So A is an even number. What will be the answers, the possible answers for A? Given the sample space above. Anastasia. Anastasia, you raise your hand.
2 or 6.
Valentina. Yes, Anastasia, say it again.
4 and
2 or
6.
6.
Sorry?
2, 4, 6.
2, 4, 6. Very good. 2, 4, 6. So these are the even numbers that you get. So they represent event A. What about event B? What does the word at least stand for? What symbol can you use for at least? What symbol can you use for at least? At least. Jessica.
Greater than or equal to.
Very good. Guys, if you don't know, write it down. Okay. At least you can use the symbol called greater than or equal to for it. Okay. Greater or equal to. Now, with that in mind, what would be the element of the number road is at least 4? B, what are the elements of B? You can tell me all the elements of B. Valentina.
Sir, please, 4 and 6.
Is that your final answer?
Yes. Oh, sorry, sir. 4, 5, and 6.
So that's why you should always double check.
Yes, please.
There
Thank
are
you.
people here, they are looking for your downfall. The moment you said that, they all raise their hands back.
Thank you, sir.
So the numbers are 4, 5, and 6. Keep those two events in mind because I'm going to ask you a series of questions based on those two events. So write them down, everybody. The first event is 2, 4, and 6. The second event is 4, 5, 6. Now, so these are the elements. On the basis of this, if I were to ask you to find the complement of A, okay, so we write A bar. What would be the complement of A? And the way to write this word complement of A is just do A bar equal to, put it in the set here. What is going to be in the element of the complement of A? Now that you know. Okay. Guys, follow some and say some. Amina.
1, 3, and 5.
Why?
Because the sample is S, which is 1, 2, 3, 4, 5, 6. And the set A is 2, 4, and 6. It means that 1, 3, 5 cannot be found in the set A, but can be found in the sample space.
Very good. So the complement of A is 1, 3, and 5. What is a complement of B? What is a complement of B? What would be the complement of B? Can you? What is a complement of B? Emmanuel.
Yes, the complement of B will be 1, 2, 3.
1, 2,
2, and 3.
and 3. I'm sure your colleagues will all agree with you. So that is fantastic. Now let's go to another term. What is the A intersection B? What is A intersection B? What is A intersection B? This is interesting, eh? Yes, no.
4 and 6.
Is that your final answer?
Yes.
Are you sure that's your final answer?
Yes.
Good, excellent. So that is correct. It's 4 and 6. Okay. Now that is obvious. That is obvious. That is A intersection B. A intersection B. Now I have a question for you. What is A complement intersection B? Write that. What is A complement intersection B? This is a tough one, but I know someone is here. Someone who is not copying, that is following. What is A complement intersection B? And I'm going to let you explain, not only give me the answer. What is A complement intersection B? Rama?
Hello, sir.
Yeah.
Yeah, A complement intersection B is 1 and 3.
Why?
Because so you're looking for the intersection which is 1 and 3, which are common in both set A and set B. And then hey, I've just lost my train of thought.
That's why I asked you to explain.
My train of thought. So let me regroup and come back. Everything
Regroup,
just
very
left my
good.
head.
Let's go to another person. Emmanuel Obiri.
Okay, sir. So the numbers we have for A complement is 1, 3, and 5. And then the numbers we have for B is 4, 5, and 6. So the intersection of A complement and B will be 5.
Exactly. You see, if you analyze it step by step like he did, you get it. But if you want to give the answer back, that one you'll be stuck. You have to break them down. Simplicity is the ultimate sophistication. Leonardo da Vinci. That's what he said. Now let's look at A union B. Okay. So let me first say that A complement intersection B is going to be 5. Now, how about A union B? What are the elements of A union B? A union B. Amina.
A union B is 2, 4, 5, and 6.
Is that your final answer?
Yes, please.
Now, sometimes when I ask you, is that your final answer? You double check to see, is it because I'm wrong? That's why that is correct. So it's 2, 4, 5, and 6. 2, 4, 5, and 6. Class rep, I want to make you listen so that you can mute some of the people when their noises come. Now let's go to, yes, Stella.
Sir, please, I'm wondering why the A union B is not 2, 4, 4, 5, 6, 6. Because you have the 4 appearing 2 times and the 6 appearing 2 times.
Yeah, when they appear twice, you take only one. When they appear twice, it's the same thing.
Okay, sir. Thank you.
All right. The next one is A union A complement. That's the last one. A union A complement. What is that? What is A union A complement? Double check. Break it down. Break it down. Break it down. A union A complement. Anastasia. Emmanuel.
Okay, so yes, sir. So for A, the content of A is actually 2, 4, and 6. And then A complement is 1, 3, and 5. So A union A complement will be 1, 2, 3, 4, 5, and 6.
Exactly. So to be everything, So it's just like he telling you that I want you to tell me A and tell me everything that is not in A. So it's everything. Okay? So I could have asked you, okay, that prove that this is equal to the universal set, and it is equal to the universal set. It's equal to the universal set. It's equal to the set. So these are some basic properties of probability that you need to master. I don't think this was too difficult, was it? Because this is a stepping stone for other great things to come. Everything that we did, let me just clean this. Everything that we did here, in fact, if you are writing them, it will be nicer. If you are writing them, it will be nicer. So this is.
Sir, please, I have a question.
Go ahead.
So in that light, can we say that any sets complement, any set union is complement is the universal set?
Any set union, yeah, exactly, it's a universal set.
Okay.
Yeah, that's the last sentence. But then a complement of A and the complement of B is not necessarily the universal set. Okay. I mean, this is true. What you have here is true, but that is not the same as A complement union B complement. Who can tell me why this is not equal to the universal set? Who can tell me why this is not equal to the universal set? Yes, Anastasia, are you sure you are here? Because anytime I call, you don't respond.
I was having a problem with my microphone, but I'm okay now.
Is it better now?
Yes, it is.
Okay, go ahead.
So the A complement has 1, 3, and 5, and then B complement has 1, 2, 3. So if you are finding the union, it will be 1, 2, 3, and 5. So it doesn't necessarily have all the numbers as that of the set.
Yeah. Well, you are right in using this example, but I'm even talking about generally why that is not equal to. You are right. What you said is fantastic. But why is it that even if you didn't know the numbers, it still won't match? Because, yeah, who can tell us? Enoch.
So because that since you are excluding A and B, that means their intersection is what is supposed to be taken as the answer. So A complement union B complement is like what is not in A and what is not in B. So the intersection of it will be the answer for it. I don't know if I'm making sense.
Yeah, you are making sense to me. I wonder if you are making sense to them. Yeah. Stella, what do you say?
So I think the A complement, how do you say, A complement union B complement is not the same as the universal set because there's an intersection. They have common elements in both sets.
Yeah. Very good. Similar. Very good. So keep that in mind because in an exam situation, this is maths. Okay. These are some things I can ask you. All right, let's move on. If you understand everything we've done so far as well. Now let's go to mutually exclusive event for this same thing. Suppose I ask you that looking at this, looking at what you have now, mutually exclusive event. If A and B, okay, if you look at the content, event A and event B, if they are not mutually exclusive, what will be the outcomes? If they are not mutually exclusive. If they are mutually exclusive, okay, it means that they can't happen at the same time. If they are not mutually exclusive, what to be? Tell them. Yes, Valentina.
So if they are not mutually exclusive, that means they have an intersection.
And that is?
And so the intersection would be, sir, please a minute. 0.6.
Exactly, it's 0.6. So understand, if they are not mutually exclusive, guys, it means that there is an intersection. And if there is an intersection, you just find the intersection. So instead of asking you to find A intersection B, I could have asked you find the event defining the non-mutually exclusive event of A and B. And then somebody will say, Mewo, but that's the same thing. So the outcomes of that is 4 and 6.
Sir, please repeat the question.
I was saying that tell me the numbers that represent the non-mutually exclusive event of A and B. Or better still, the joint effect or the joint event of A and B. Because events which are not mutually exclusive means they are joint. Write it down. You see, these are some of the notes. Not mutually exclusive means they are joint. Mutually exclusive means they can't happen at the same time. So they are not joint. So there is no intersection. But when there is an intersection, there's a joint. And when there's a joint, there is no mutual exclusivity. Should I slow down? Another thing about probability is that sometimes it can be confusing. So if you want me to slow down, you say it.
So please, could you repeat that again?
Sorry?
Could you please repeat that again?
Okay.
So
events that are mutually exclusive means that there's no intersection. Write that down. There is no intersection. Mutually exclusive. They can't happen at the same time. See, as you can see, there is some numbers that are happening at the same time in A and in B. 4 is inside A, 4 is inside B. 6 is inside A, 6 is inside B. That means that A and B are not mutually exclusive. They are joint events. They are joint events. Something is between both of them they share in common. Now, when that is the case, and I ask you, tell me those events that are non-mutually exclusive. The elements of the non-mutually exclusive event, they are 4 and 6 in this context. It is what is common to both. And I'm saying that events that are mutually exclusive don't have what? Intersection. Write that down. They don't have intersection. Okay? Because they are mutually exclusive. They look like a circle on its own here, a circle on its own. No intersection. But events that are mutually exclusive, they have what? They have an intersection. And when they have an intersection, the intersection is what makes it non-mutually exclusive. Because that intersection is joint. So they join together somewhere. So sometimes somebody say, I have my half brother. And then the same person will say, he is my brother, he is my half brother. And then there's another one. Apart from the half brother, you know there's another one. What's the other one? Step brother. You know there's a difference between step brother and half brother. I guys are aware. Don't worry. You can ask DeepSeek. So there's a step brother, and there's a half brother, and there's a brother. Some of them are non-mutually exclusive. See, a brother means that they come from the same mother and the same father. Yes, Stella.
Yes, sir. So as per the explanation you're giving, if we are asked to find the event which represents the mutually exclusive of A and B, that would make A 2 and B 5, if I'm right. I want to be sure I understand.
A2 and B5.
And B would be 5.
No, the thing is that A and B are not mutually exclusive.
Okay, just because of this situation, sir.
Just because there is an intersection, there's a marriage between A and B. So the two events are not mutually exclusive events in the first place. It's not the element. It's not the element. It's not the things inside. But it's rather the circle that is the event. And so mutually exclusive event is a circle. So this circle is an event. 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 So I have circle A, circle B, circle C, circle D. And now I can have this circle again. So this is D and this is E. All of these are events. Okay. So A and E are non-mutually exclusive events. A and B are mutually exclusive events. Are you aware? A and B are mutually exclusive on the screen. Do you agree?
Yes, sir.
Why are they mutually exclusive events?
Sir, they don't have any intersection.
That's it. A C and E mutually exclusive. C and E, are they mutually exclusive or not, Anastasia?
No, sir, they are not.
They are not. They are mutually exclusive. C and E are mutually exclusive. D and E, are they mutually exclusive or they are not mutually exclusive? D and E. Amina.
Can you please explain the C and E for me, please?
C and E are mutually exclusive.
Yes, they don't have any intersection.
Yeah.
Okay.
So now I come to D and E. Are they mutually exclusive or they are not mutually exclusive? Emmanuel.
They are not.
They are not. How about C and D? How about C and D? Are they mutually exclusive or not, Valentina?
They are not mutually exclusive.
Good. So they are not mutually exclusive because they have an intersection. So guys, understand these things. So is a brofo. What can check? So there's sometimes the English can. Okay. Now A and B, okay, are they collectively exhaustive or they are not collectively exhaustive? Okay. Are they collectively exhaustive or they are not collectively exhaustive? Okay. When you look at A and B, do they contain, okay, so first, are they collectively exhaustive? Okay. And I'll ask you why. So before you raise your hand, think of the why. Nanama.
No, they are not.
Why?
And this is because when you add both A and B, there are still numbers that are part of the universal set that's not part of A and B. So you can say that both of them combined are not collectively.
Exactly. So both of them combined are not enough to match the universal set. That's what we mean by collectively exhaustive. So when I give you some two events and I ask you, are they mutually exclusive or not? Are they joint or not? Are they collectively exhaustive or not? You should be able to explain why and why not.
Hello, sir.
Yep.
Please, can you repeat what you said about the collectively exhaustive when you're saying
Nanama.
you said
It's
both?
Nanama who said it. Nanama said, explain.
No, you gave a certain explanation. Another way to
Yeah, what I'm saying is
saying
that collectively exhaustive means that when you take the element of A and B and you combine them, they have elements. When you combine them, there are still things they don't have, but it is in the universal set. Even when you combine them, there are some numbers that are in the universal set that their combination don't have. That means they are collectively not exhaustive, or they are not collectively exhaustive. So to be exhaustive means that you have everything that is in the universal set. You have everything. For example, A itself is not collectively exhaustive. B itself is not collectively exhaustive. Both of them combined are also not collectively exhaustive on their own. Please, does that make sense?
Yes, sir.
All right, okay. So let's continue. These are all basics. So let's get into probability itself. What is probability? We said it before. Probability is a likelihood of an event happening. Okay, the event happening, or the chances of the event happening is between 0 and 1, or it is 100%. If it is 100%, it means you are certain that this thing is going to happen. If it is 0, it means that it's impossible for the event to happen. Okay, the weatherman uses a lot of probability. If it is 50%, if the probability is 50%, it means that the chances of happening is at the middle. Whether an event will occur, whether you will finish this course cum laude, whether you'll be able to graduate cum laude, whether you'll be able to give birth this year, all of these are events. And we can assign a numerical value to them. They are chances of happening. We can assign that numerical value. And there are three major aspects of probability. There are three types of probability. So watch it. The probability of A is the summation of all the individual probabilities, just as I gave here. So if you have if you sum all of them, you get the total. In fact, when you sum all of them, you should get 1. Let's look at the 3 types of assessing the probability of an event. You can use something called classical probability, relative frequency probability, or subjective probability. What is it all about? Okay. Let's take, for example, let's assume this is a classical one. All the outcomes are equally likely to occur. That's classical. Okay, that's like a random. If I close my eyes and I try to pick different balls in a basket, the chances of me picking any ball is what? Each one has got a chance of being picked by me. So classical probability considers the likelihood of equal likelihood of the event, okay, each one being collected. How do you calculate that? You calculate that by taking the parts divided by the whole. So the probability of event A is the number of the outcomes that satisfy the event A, NA, divided by the total sample size. It's a very simple, it's the simplest and the easiest one. But what it does is that it requires you to count, okay, the outcomes in the sample size. You've got to count it with your eye before you will know the total. And then you will also know how many times this thing is happening. The next one is a relative frequency probability. It's a very simple one as well, because that one looks at the NA divided by N. So what is the difference between the first one, which was capital, and this one? Well, the NA means the number of events in the population that satisfy event A, divided by the total number of events in the population. What is the difference between this one and the previous one? If you look at the previous one, we are looking at the number of outcomes that satisfy event A. This one looks at the number of events in the population that satisfy event A. What is the difference? Both, the one is looking at something and the other is looking at something. It's a very, very simple comparison. Yes, Valentina.
So one is looking at the number of events. So it's looking at the events, and the other one is looking at the outcomes of the events.
Mm-hmm. Very good. Do you all agree? That is the key point. Not the event, but then the outcome of the event. So one is looking at the number of the event itself, and one is looking at the number of the outcomes. You can have an event, which is a football game, and the outcome is what you're looking at. So normally, when you are looking at a tournament, a football tournament, the moment you lose one game, you are now calculating, what's the next game we have? You have 2 more games. Okay. So you're more interested in the number of events there. But most situations, you're looking at the outcome of the event. How many goals did you score? And things like that. I didn't get to many. All right. Let's go to the last one, subjective probability. As the name sounds, it is an individual's opinion. The subjective means that it's not me, it's my opinion. My opinion. So it's very, very simple. Very, very simple probability that we look at. Okay, now we get to the rules of probability. Because you see, the reason why probability has got a lot of rules is because you are not sure of the outcome. It's a guess. Sometimes they call it conjecture, I guess. So let's look at the rules. The first rule is the complement rule. We've already looked at it. The probability of a complement of A, event A, is 1 minus the probability of the event A itself. That's a rule, a very simple rule. I write it down. Sometimes when you write the rule down, that's when you remember it. So if you do change of subject, if you move the probability of event A to the left-hand side, then we can say that the probability of event A plus the probability of its complement will be equal to 1. Very simple rule. But you will need that rule in some calculation. Then the next one is the additive rule, sometimes called addition rule. In the addition rule, the probability of the union of two events is set to be the probability of event A plus the probability of event B minus their probability of their intersection. Guys, pay attention here. And the only way you can pay attention is writing these rules. So watch it carefully. For such an event to happen, then the event must be what? Who can guess? For this rule to happen for such an event, then the event must be what? Is it mutually exclusive or non-mutually exclusive? Nanama. Nanama, now you are confused.
Sorry, no, it's supposed to be non-mutually exclusive.
Are you sure?
Yes.
Are you very, very, very sure? See, I'm
Because
asking
if
you.
it's because if it is not non-mutually exclusive, we won't be able to subtract that the intersection from the probability of the event.
For that to happen, we'll see. We'll see how powerful your answer is. But keep this rule in mind. Okay? It's very important rule. Very, very important rule. So guys, let's take a typical example. And to do that, I'm going to use a deck of cards. Please, have you all remember SPA? Do you all remember SPA? SOPA. Okay. Now, before I come here, let me just give you a story about the deck of cards in case you remember. You know, we have a name for each of the symbols. There are 52 cards in a deck of cards. And they have 4 different symbols. Do you know the name we have for this symbol? I mean, we have a very strange name for it in Ghana, but then there's a proper name for it abroad. Okay. Abroad, they call this one a different name from the one, but we call it this what? Those of you like to play. What is the name for this one? This first one. What's the name we call it? Oh, come on. Who can remember? What are the elements of the deck of cards? Okay, Theophilus.
Say love or
So, what?
love.
Cloud.
Love or heart.
Yeah, but it didn't know first. I said, what name do we call it first? We used to have a name for it. The heart is the universal name for it, but we call it what? This one, if you have been playing with it, you know, Emmanuel.
We call it yet.
Exactly, we call it yet. But then the actual name is heart, okay? And it is always red in color. That's why you see it like. The next one, okay, the second one, what name do we normally have for it? It's a very funny name, eh? Before we look at the universal name. Who remembers the funny name, Enoch?
Says, SPA. Is it SPA?
No, Master, it's not SPA. If you don't know, say you don't know, then you don't raise your hand and come and confuse us. Andrew.
Say crane.
Kulei. Okay, that was the name we used to give to it. Kulei. Okay. The actual name is what? Ima.
Clubs.
Clubs. Okay, so that's the clubs. Now the next one, what was the name we used to call it? It's a very funny name. That starts with, you know, it's very, very funny. Enoch.
Say Carlo.
Carlo. But what is the actual name, the universal name?
Diamond.
Diamond. Okay, it's a diamond and it's always red as well. And then the last one, what name do we normally call it? That one is the closest one to the universal name. Andrew.
SPA.
SPA. And the universal name is what? Universal name. Ima.
Spades.
Spade. Guys, if when we were talking, you weren't writing this, you're in big trouble. when we were talking, you were not writing this. I promise you are in big trouble because we are going to use those terminologies throughout. So when we start using terminologies and you start getting confused, it's because you didn't write them down. So take note of that. Theophilus.
Sir, please, are you saying even the local terminologies? Are you going to include
No,
that?
I'm talking about the universal terminology.
Oh,
so
okay.
you have the hat, you have the club, you have the diamond, and then you have the spade. The hat, the club, the diamond, the spade. Keep that in mind. Okay. Now, when you take each one of them, they also have other things. For example, so first of all, you can see that we have 4 different suits. These things are called suits. They're all the terms we have mentioned. Okay. Now, there are ranks. Okay, there are ranks in them. Okay, and we have some of the ranks like aces, okay, or aces. And then we also have the face cards. The face cards are the jack, the queen, and the king. How many jacks do we have? How many jacks do we have? It's all down on your screen. How many jacks are there? Amina?
4.
There are 4 jacks from each of those suits. There's a reason why I'm going through this with you. How many queens are there? How many queens? How many kings? Amina?
4.
There are 4 queens. There are 4 kings. Okay. Very good. Now, how many red hats are there? How many hats are there? How many hats? How many diamonds? How many clubs? How many spades? Each one of them carry how many? 13, 13, 13. Okay, so 26 of the cards are red, don't forget. And those ones are the diamonds or the hearts, as you can see on top. Okay. And 12 of the cards belong to any of these 4 suits. Okay. And then the other 4, making up the 13 for each one, they are the S's. 6 of the face cards are red. 6 of them are red. Okay. Because in total, they are 12. So 6 of them are red. They are the diamonds on the heart. And 6 of the face cards are blacks. They are the spades and then the clubs. And then we have 4 S's. So that's it. Look at it now, finally. This is a deck of cards completely done. Have a feel of everything here. Now, are you ready for the questions? Question number 1. So the first question is, we're going to the question, actually. The question is up here. So, why don't you ask the question? Okay. So if you look at this one, what is the probability of having a red or an essay? What is the probability of having a red and an essay? Or let's put it this way. What is the probability of having, let me just write it here. What's the probability of having, the thing is not writing. What is the probability of having red union essay? Red union essay. You can tell us. The probability of having red union essay. Now, you don't know any of them. So what is the probability of having red union essay? You're going to use additive rule to do this. So first, red union SA, remember the additive rule? Just go back here. The additive rule say if you have A union B, you apply probability of A plus the probability of B minus the probability of A intersection B. Okay, so when you come here, what is the probability of red union SA? How many reds? Oh, first of all, how many deck of cards are there? You should have the universal in mind. How many deck of cards are there? Yima?
52.
Put that in your mind. Okay, if you are here, you are not writing that, put that in your mind. So you need that 52, first of all, in the mind. So we're going to have 52, which is the denominator. Now, the probability of having a red, how many reds are there? How many reds are there? Ima, Lamte.
The reds are 26.
Good. So you have 26 over 52. Then the additive rule, because we are talking about union, is to add them. How many S's are there? How many S's are there? Oh, yeah, you can see them. They are not the first column. How many S's? Obri?
We have 4.
Good. So you have 4, and they divided by the universal set. Then according to the rule, you should subtract the A intersection B. Now, A intersection B here will be the red union, sorry, the red intersection SA. So when you look at the reds, how many of them are S's? It's simple. When you look at the reds, how many of them are S's? Lamte.
2.
Sorry?
2.
You get 2, exactly. So this is how you're going to find your probability of red union S's. When you do that, what do you get? When you cancel, you're going to get, say the denominator is the same, you're going to get 24. Okay. So you're going to get 26 plus 24 minus 2. That'll give you 28 divided by 2. And that is your A union S. So this is it. It's very important. So I can ask you 100 questions on probability using a deck of cards alone. This is how you find. I just gave you the thing, okay? But so if I have asked you what is the probability of getting red union S's, this is the way to go around it. Any question? Any question? Remember that this deck of cards, sometimes you have some jokers, in some specific games. You have some jokers. Sometimes you have some advertising cards and rule cards and all that. But they are not usually part of the play. Okay, let's go to the next one. The next probability is conditional probability. Now we're getting deeper. Okay? We're getting deeper, but we're also getting to the end. I want you to understand conditional probability today more than any other probability we are ever going to do. Conditional probability. What is that? Conditional probability. Now, the word conditional, give me another word for condition. Conditional. I will give you the money conditioned on the fact that, so what is conditional? Conditional require you to have done something to be able to get something. That's conditional. You're required to do something before you can. So conditional probability is a probability of one event given the other has already occurred. Guys, pay attention here. The conditional probability of A given B, look at it carefully, look at it all, is the probability of A intersection B. Somebody is writing, let me just disable this writing. Okay. Is equal to the probability of A intersection B divided by the probability of B. Now remember, the B here is the one that comes to the bottom. Okay. That is because the B is at the end here. So when you have probability of A given B means that B will come to the denominator. And when you have probability of B given A, because A is the one given here, A comes to the denominator. Take note. But the numerator doesn't change. It's still probability of A intersection B. This is what is known as a conditional probability of A, given that B has already happened. Write it down. Write it down. Even if you know it and you have the note, write it down. Because as you write, it sticks into your mind. All right, keep that in mind. You're going to think along this formula. Let's take a real life situation. Out of the cars on a used car lot, 70% of the cars have air conditioning, AC. Pay attention. 70% of the cars have AC. 40% of the cars have CD player. 20% of the cars have both AC and CD. What is the probability that if I should close my eyes and pick a car at a random of the number of cars, what is the probability that a car that I select has a CD player, given that it already has an AC? This question quickly should tell you that you are dealing with what kind of probability? Who can tell us? This question should tell you that you are dealing with what kind of probability? Stella.
A conditional probability.
What gives you the clue that is a conditional probability you're dealing with?
We have been given that it has the AC, that another event has occurred. So the other event is the AC.
So what is a key word here?
Given that.
Exactly. So you look out for the keyword, and the keyword is given that. And once you know that given that, you are flying. Now, once you know that it's about given that, then you have to quickly think about the formula for the conditional probability. So you got to take your time and write the elements that conditional probability says that you are looking for the probability of A given B, and this is supposed to be probability of intersection of A and B divided by the probability of B. So you got to write that thing down. Watch the question. It says that given that it already has AC, when you are writing, you have to write it well, because sometimes you don't take care, you go and switch the writing. You are finding the probability that a car has CD given it has AC. This will be equal to what? Who can tell me? This will be equal to what? Given what we said before for the previous one. This will be equal to what? How will it look like? So the probability of CD given AC will be equal to probability of what? Should I go back so that you see how it was here? Manama.
So it will be probability of, so P bracket open, CD intersection AC bracket close all over probability of AC.
Fantastic. Well done. See, you can see that she has eaten before coming here. So it's a probability of CD intersection AC divided by the probability of AC. That's it. So this is what we mean by the conditional probability. So now you get it. Okay. So we need to find the probability of CD intersection AC. According to this question, the numerator is equal to what? The numerator, according to this question, was equal to what? Lamte.
20%.
Good. So that is 0.2. The denominator is what? The denominator, according to the question above, what is the denominator? Jessica?
70%.
70, that is point that. Therefore, what is our conditional probability of CD given AC? tell us. Jessica.
0.285. That's
I want you to finish. So 0.2857.
57, yes.
So it means that the chances of you finding any card that has CD player, given that it already has an AC, is 28.57%. The chances are not that much, but it's a good chance. This is it. Learn how to interpret the thing. The likelihood, the probability of getting is 28.57. Correct to the 2 decimal place, it means that we are talking about 29%. Finish. This is an example of a conditional probability. Everything we did is here. Whilst this thing might be a little bit, you don't care because you got the point clear. That's it. Who has a question? Who is not clear? Now let's look at, so remember, this is called conditional probability, but there's, yes, Stella, hand is up.
I wanted to know if the question will always be clear enough for us to see that we have a condition in the question.
Oh, yeah, yeah, you
always be clear. Okay.
It will always be there, it will always be there. That one will always be there, but there can also be multiple conditions rather given to you. So that's what the condition you get, but you can also have multiple conditions. But let's go to the multiplicative rule, because all that we've done is additive. Anastasia, what's your question?
Yeah. So the answer should always be in percentage, right?
It's nice. It's nice when you leave it like that. When you leave it in percentage. It's nice when it is in percentages. Please, is that fine by you? Yeah, just multiply the answer by 100% and yes, you're good to go. Okay. Now, multiplication rule for two events A and B is that, see, from here, you can even deduce it from the previous one. Look at it from here. Okay, from this one here, you can do a multiplication. The probability of A given B can cross multiply probability of B. And so the probability of A intersection B will be equal to the cross multiplication of that. And the multiplication rule says that the probability of A intersection B is the probability of A given B multiplied by the probability of B. Okay, watch it here. The probability of A intersection B is the probability of A given B multiplied by the probability of B. So it's just cross multiplying the conditional probability and you have the multiplicative rule. Guys, are you with me? This is it. And of course, the other one is the same as it. Write the conditional probability. It's very important. But you see, sometimes the reason why we have given two of these formulae is that you got to know where it is coming from. You know, sometimes it's probability of A intersection B. And you have the ordering. The ordering are very important because probability of A given B is different from probability of B given A. So if you look at this top one, it's different from the down one. Whereas the top one is looking at probability of A given B, the down one is giving probability of B given A, and they are not the same. They are not the same at all. At all. All right. Let's take a real life situation.
Hello, sir. Kindly repeat what you just said for me.
I said that the probability of A given B is not the same as probability of B given A. The probability that you have a CD, given that you have an AC, is not the same as probability of having an AC, given that you have a CD. But that is also why this is multiplying the probability of B. and this is multiplying the probability of A for that intersection to happen. Because if this intersection on the left, okay, if this intersection on the left is the same as this intersection on that, then it means that the idea is that this one is also supposed to be equal to that. It is by the principle of the Bayesian theory or the Bayes theory. We'll come back to that, but I just wanted to know that this and this are not the same. And so for the equality to happen, then this one must multiply this, whereas this one is multiplying this. It is the equality, is the multiplication here that are equal, but not this one and this one that are equal. That's what I'm saying. Please, do you get it now? I'll give you an example for you to appreciate it. Suppose I say this is 20 and this is 20, okay? And in here, I have 10 times 2, okay? And in here, I have 5 times 4. Are they all equal to 20? Are they all equal to 20? Yes.
Yes.
Yes,
sir.
Yes, sir.
So if they are all equal to 20, because this one is the same as this down one, you might be tempted to say that this and this one are the same, but they are not the same. And you'll be tempted to say that this and that are the same. They are also not the same. But then their products give the same values. That's what you see on the left-hand side. So I'm just telling you that the probability of A giving B is not the same as the probability of B giving A. But once it is multiplied by probability of B, and once this one is also multiplied by the probability of A, they will both be equal. Anyway, I think you get it. So, remember the deck of cards again? Let's go down here. Okay. Let's look at the probability of having a red intersection essay. Okay. In the deck of cards, let's find the probability of having a red card intersection essay card. This is interesting. It's a very, very simple thing. Now watch the formula for the probability here. This is multiplicative rule, and this multiplicative rule does not require you to add anything. You are only multiplying using the multiplicative rule that we just gave. Okay? And again, this rule is what we are saying, that something intersection something, an event A intersection event B, is the conditional probability of event A giving B multiplied by the probability of B. So when you have this, probability of red intersection probability of SA is the probability of red giving SA multiplied by the probability of SA. Okay, what is the probability of red? Sorry, what is the probability of red giving SA? Okay. So first of all, the word giving SA means that you must know that there is already an SA. How many SAs do we have? This one is a quick one. How many SAs in the deck of cards here? How many SAs do we have? Ima?
4. 4, sir.
And then how many of them are red? That's the meaning. How many of these are red? How many of them are red? At Japan?
2.
Exactly. So therefore, when you are talking about the probability of red giving SA, you are just talking about 2 divided by 4. Multiplied by, what is the probability of SA? And you got to be careful with that one. What is the probability of SA? Or better still, how many SAs do you have? It's 4.
4, please.
So you divide this 4 by what? By what? What do you think? Amina?
52.
Good. And the reason why it has to be 52 is because this 4 is coming out of the 52 cards. Unlike this first one, where the red is coming out of the SA cards. So now that gives you 52. So you can now find the multiplication of this. If you do it well, you're going to, in fact, even if you cancel here, 4 cancel 4. And so you are left with 2 over 52. And so that is an example of a conditional probability. When you check this, it is all here, this conditional probability. Very simple. Very simple. Okay. Now, let's go to joint probability. Okay. Joint probability or marginal probability. If I say that the probability of a joint event, okay, a joint event is an intersection. And a joint event is what we have looked at, but we looked at it in a multiplicative form or in a conditional form. Now we are looking at it in a marginal form. Marginal here means that you have something divided by something, that's it. So the intersection of A and B is a number of the outcomes satisfying A and B divided by, okay, Emmanuel and Amina, if you don't have a question, leave your hands. Divided by the total number of elements. Okay. Well, if you want to compute the marginal probability of an event, it's just adding all of them together. This is easy. This one, there's no wahala about it. Marginal probability is very easy. Let's take a typical example of a question on it. Going back to the deck of cards. Let's say that I want to find the probability of SA. Okay. I want to find the probability of S's. If you look at the marginal probability, if you want to find the probability of SA, you are going to have the probability of SA intersection red plus the probability of SA intersection black. Now, how do we know that? Because their colors are what? They are only red and black. They suit, they are only red and black colors. So among the red, how many are S's? And among the blacks, how many are S's? And that is the answer. So let's start. Among the reds, how many are S's? Anybody? And of course, this will be divided by the number of 52 cards. Among the red, how many are going to be S's? These are the red. Yes, Anastasia.
2, please.
2. And so this one will be 2 divided by 52. And then among the black, how many are S's? Anastasia.
2.
Therefore, the probability of having an SA, the chances of you closing your eyes and picking an SA is going to be what? The chances of you getting an SA is going to be, Stella.
4 over 52.
Exactly, 4 divided by 52. That's it. So this is the probability value that we are looking at. 1 over 26. It's a very, very simple question if you understand what you are doing. Of course, you can use a tree diagram to also calculate it. But you can use a tree diagram to calculate the one that we did. The conditional probability that we did. What's the name? The conditional, this is for the SA one. The conditional probability here. You can use a tree diagram for it. And again, you will end up with the same answer. Okay, these are all the cards. Okay. Those that have an SA, AC, okay, is 0.7. If you don't have an AC, it's 0.3. That is the probability of AC complement. Okay, so if you have an AC, what is the chance that you have a CD? Is 0.2 over the AC. If you don't have a CD, it's 0.5 over that. Okay. And then if you have a CD, but you don't have an AC, it is 0.2 divided by 0.3. That's on the complement size. Okay. If you don't have a CD, it's 0.1 over 0.3. And so that will give you all of these possible answers. So, but as most of the time, you will like the previous one. We're going to go to the end of our meeting for today, looking at the Bayes theorem. It was postulated by Thomas Bayes in the 1700s. It is a foundation of probability. If you are ever learning probability, you must know about the Bayes theorem. It's a little bit tricky, but you guys are smarter. So just pay attention. If you can get this Bayes theorem today, I promise you, you have understood everything. This theorem, you've understood everything. So let's start. I want you to pay attention, and please, when we get to the theory, try and write it down. Let A1 and B1 be two events. So there are two events, A1 and B1. What Thomas Bay said is that if that is the case, then this probability of A1, or you can just say A, you know, but the probability of A given B is equal to the probability of B given A multiplied by the probability of A all divided by the probability of B. Forget about the second one. Look at the top. Now, this reminds you of what? Can tell us. This thing that you are seeing at the top here, it reminds you of what to rule or what we have already considered. What does it remind you of? Valentina.
Conditional probability.
Thank you. So what do you think he has done to the conditional probability? He has revised it. He has revised it by using, additional information. And I'm telling you, the revision is beautiful. Let's understand the revision first. So first thing, the conditional probability is this. That's what you see on the screen here. This part here is a conditional probability. The conditional probability of A given B is the probability of A intersection B. Remember, I said the conditional probability of A given B is the probability, I didn't say it's a conditional probability, is the probability of A given B divided by probability of B. Okay. We know this. We know that. But here we can do something interesting. Watch it carefully. Watch it. We can swap B and A. We can swap B and A. So wherever we see A, we put in B, and wherever we see B, we put in A. You can do that. I'm just trying to show you the derivation, how we came out. That's the first thing. The second thing you should take note of this is, you know that the A intersection B itself is the same as B intersection A. Are you aware? So this A intersection B here is the same as B intersection A. That rule doesn't change. Let me put that down for you to see. Okay. So, okay, let me put it all down so that you can appreciate it. Sometimes when you put it down. So we can swap wherever you see A, you put in B, and wherever you see B, you put in A. In fact, that's the same thing. That is more or less here. But the key point is the numerator part. I want you to know. So from here, we know that this A intersection B is the same as this B intersection A. We know that. So wherever we see this A intersection B at the top here, we will put in the B intersection A. So take note of that. Therefore, watch it. First, I can now write this one, swapping the A and B. Okay, I can rewrite these two, which is swapping the A and B. And then I can say that wherever there is B intersection A, here, what will I have? Wherever there is B intersection A, I can now have A intersection B. Can't I? I can have it. So watch here carefully. So at the top here, after swapping, here I will replace it with that one there. I'll dump this one here. So what are we left with? We are left with B, probability of B given A, and then the numerator is going to be what? Probability of A intersection B, isn't it? Instead of B intersection A. It's going to be probability of A intersection B. And then divided by what is already there, which is probability A. Guys, are you with me? I am just taking this first one here. Let me clear it. I'm just taking this one here. Wherever I see A, I replace it with B. Wherever I see B, I replace it with A. And that gave me this. So this one gave me that. Then at the top, because of this rule here, I just substitute this one and I put it at the top. So what are we going to get? We're going to get this very thing down here. So now you have probability of B given A, that's what is here. And then at the top, instead of B intersection A, I'd rather have A intersection B. And then all will be divided by what? A, which is what I have. Now, with this one here, we have achieved a beautiful scenario. Because we can cross multiply at this stage, can't we? If you cross multiply this by that, then we are saying that this probability of A intersection B is a cross multiplication of that. So watch it. If I multiply probability of B given A multiplied by A probability of A, I'm going to get this. So that's probability of B given A multiplied by probability of A. And that should be equal to this top part. You know what is interesting here? You know what is interesting? What is interesting here is that wherever, watch it, wherever I see, because this one means that wherever I see probability of A intersection B, I can replace it with this. Therefore, I can move this last one here. I can move this last one here, move it, and boom, and put it here. Because it is actually saying that anytime I see A intersection B, probability of A intersection B, it is referred to the probability of B given A multiplied by the probability of boom. I can drop it here, and therefore the probability of A given B will be equal to this very part here. We'll replace that one. That is a probability of B given A multiplied by the probability of A, all divided by the probability of B. And this would then match that, which is a Bayes theorem. I know you get it slightly, but I also know that when you eat your bangu, you'll get it better. I know. But it's all here. So in short, what are we doing? We can derive the Bayes theorem from the conditional probabilities. That's all. It's a matter of rearranging the conditional probability, and you have your Bayes theorem. It is simple. But of course, if it's not simple, you just go through it and you see that's simple. Yes, Valentina.
Please, from your last statement, you said we can derive the Bayes theorem from the conditional probability. If I'm right.
Yes.
Okay, because when you were swapping, I saw that there was also multiplication probability at the latter end.
I was cross multiplying.
Okay, which is actually what we do under the multiplication rule.
Under the multiplication rule. Watch here. This multiplication rule.
Yeah.
Yeah, but the multiplication rule, we don't really cross multiply. It's just equal to. But you can say that cross multiplication is the multiplication rule. That's what you mean?
Yes.
Yes. That cross multiplication is the multiplication rule. Well, it is multiplication rule because it's cross multiplication. So yeah.
Okay.
But even if you don't know the multiplication rule, mathematics will tell you that when you cross multiply, it's equal.
Yes, sir.
Because here, mathematics tells me that if I divide both sides by the probability of B, I will get this one. So with this Bayes theorem, it's a very powerful thing. But what I've given here is a general one. It's a specific one for two events. But when the events are multiple events, then you are talking about a lot of them like this. So where EI, the event is a particular event out of all the K mutually exclusive events, also collectively exhaustive, then in that case, you're going to have a lot of additions here. A lot of additions. So this is a general case of the Bayes theorem. I think an example will do. Let's take an example. This will clear the air, provided you are follow. So let's look at the story. Someone should read the story for you. Who is going to read? This story is a kind of an exam question. Who can read it? You saw this? Valentina.
A drilling company has estimated a 40% chance of striking oil for their new well. A detailed test has been scheduled for more information. Historically, 60% of successful wells have had detailed tests, and 20% of unsuccessful wells have had detailed tests. Given that this well has been scheduled for a detailed test, what is the probability that the well will be successful?
There's something first you want to take note, and it is this Bayes theorem for the generalized case. Watch it very carefully. That when you take this first one divided by this, you have the probability of A given EI multiplying the probability of EI, which previous one it was B. EI was standing for B. Now, if EI is multiple event, then this whole probability of A, okay, it is going to, the bottom side of this equation is going to be probability of A given the event 1 multiplied by the probability of E, event 1, plus the probability of A given event 2 multiplied by the probability of event 2, plus the probability of A given event 3 multiplied by the probability of event 3, all the way up to whichever number of events that you may have. Keep that general formula in mind because it's useful with what we are about to do. Okay, let's try and understand what we are doing here. We have a drilling company. The company has estimated that there is a 40% chance of striking oil, okay, or striking oil for their new well. So they got a new well, let's say they got a new well in Ghana, and they want to strike some oil there. The chance of striking an oil is 40%. We got to take our time and do some representations. For example, now watch that word, new well. Okay, so that's the first one. Second one is that there was a detailed test which was scheduled for one because the fact that you have there is an estimated 40% chance of striking an oil doesn't mean that you strike the oil. So you got to do a test to see whether we can actually strike oil. Now, previously, what has been happening is that 60% of successful wells. So remember that we have a new well, okay? But successful wells over the past, okay, 60% of successful wells have had the detailed test. So it means that if you want to ever have a successful well, or if you want to have want to strike an oil and you want to be successful, you must first do what? Based on that sentence here, historically now, you must do what? Amina.
A detailed test.
Thank you. So that's a condition there. Somebody were asking me that, hey, how will you know? Should you have to see the word condition? That's a condition. You don't just get up and get a 60% of successful one. You must have done detailed test. 20% of the unsuccessful wells to have detailed test. So you can still have a detailed test and you'll still not be successful 20% of the time. But the question wasn't asking you about that. So watch the word. So first thing, you have successful well, and then you have detailed test, and then you have unsuccessful well, and you have detailed test. Now, given all these, that this well has been scheduled for a detailed test, what is the probability that the well will be successful? So now you have your context. So there are some important things you want to define first. The first one is we need to know a successful well. So let's represent certain things by certain things. Okay. The first thing is that we can let S be what? A well that is successful. Can we do that? S is a well that is successful. So that's successful well. Then it means that we must also have something representing what? You can tell me. We must also have something representing what? And can make it faster. Stella.
The unsuccessful wells.
Good. So you have U to represent unsuccessful well. Very good. So now we need to know the probability of having a successful well. So we need to know something called P of S. P of S, the probability of having a successful well. And then we also need to know the probability of having unsuccessful well. Oh. What is the probability of having a successful well? Who can tell us? What is the probability of having a successful well? P of S from the question. I didn't say that the well has been detailed. I just said the probability of having a successful well. What is the probability? So watch the first sentence. A drilling company has estimated a 40% chance of striking oil for their new well. That is successful. So it's like there's a 40% chance, without even detail, no, 40% chance of successfully striking oil. That's what it means. So the probability of striking an oil, that is being successful in striking the oil, is how many percent? 0.4. Which means that the probability of unsuccessful striking will be what? What is the probability of unsuccessful?
60%.
0.6. Very good. So you have this first scenario, but they are deductible because remember, okay, 100, the whole probability go up to 1. So if one is 0.4, then the other is that has no condition attached to it. These ones don't have it. We call it prior probabilities. These ones, we call them prior probabilities. But now we have to define the detailed test event because there was a detailed test. So let's D stand for detailed test. Okay? So D is detailed test. Detailed. So keep that in mind. And now we have to define conditional probabilities. You see, this one are just prior probabilities. What you see here are prior probabilities. Prior. But now conditional probabilities. Oh, condition. Which means that it is conditioned on the fact that it is successful. It is conditioned on the fact that it's successful. If it is not, that's not. So what is, how do you even write it down? How do you write that? Watch the word. It says that a detailed test has been, so what are we, which one is the condition? So the probability of a detailed test, given that it is successful. Yeah, because remember, successful was a striking first, but once you've done the striking, then you go and do detail. Okay. So the probability that I am doing detailed, given that is successful, it was given in the question. So I'll write it that probability of detailed, given that it is successful, okay. And then there was a question that even if it is unsuccessful, there must also be a detail. So the probability of having a detail, even when it is unsuccessful, that one was also given. So the first one, the probability that you are doing detail test, even when it is successful, what percentage was that? What was the value? So watch the D giving S. This is the only part where you have to understand. Yes, Stella.
60%.
Yeah. Remember, it is detail giving successful. Giving successful. Okay? So that is 0.6. And then detailed giving unsuccessful. That one is what? Stella.
20%.
So you have 0.2. Do you know what the question is asking you now to do? So we filled in all the numbers. Now watch the question. What you see here is the probability of, you got to do a detailed test even when it is successful striking. You have to do a detailed test even when it is unsuccessful striking. So what are we looking for? It says, given that this well has been scheduled for detailed test. So you see now he's telling you given detailed test. That's what it means. Giving detailed test. So you are swapping these two. This one was, giving successful. We are doing a detailed test. Even if it's successful, it's got to do a detailed test. But this time, given that it is detailed, what is the probability that the well will be successful? So we are actually looking for the probability that well is successful given detailed. So you see the way the thing looks like. That is the Bayesian approach. The moment you see, conditions being given in that way, then you know that we are dealing with the Bayesian principle. So what are we looking for? We have to apply Bayesian theory. Yeah, Mavis.
I'm a bit confused. So can you hear me?
Yeah, you can go ahead.
Hello?
Yes, go
Can you
ahead.
hear me? Okay, I'm a bit confused. It says, what's the probability that the well will be successful, given that you've been scheduled for a detailed test? So I was thinking it would be PS over D instead. So probability of success given detailed.
Which one? That's what I've written. You see, probability of successful given detailed.
Oh, okay.
That's what we are going to find.
Okay. Yes, I'm fine.
So we're going to find this, and to find that, we got to apply the Bayesian, because now we are going to have probability of successful given detail. Now, probability of successful given detail will require that you have to, remember it's P of S given D. So that should be equal to the conditional probability that we have. So I would say that will be equal to P of, and if you can remember the condition, P of D given S, okay, multiplied by P of S, the probability of success. Again, if you can go back to this rule, okay, just go back. You can go back to this rule. You can see that P of A given E multiplied by the latter one, the probability of E. So that's the same thing I'm using here. P of S given S, then you now have multiplied by the probability of what? S. That's the numerator. Divided by, then we go to the denominator. Remember, the denominator will have the same thing as the top. Nothing will change. And again, in case you've forgotten, let me just take you back here. The denominator here, watch the denominator. In fact, take this one, it's the same thing here. Okay. And watch the denominator, P of A given EI multiplied by probability of EI. It's the same thing come first. P of A given EI or E1, in this case we know, okay, multiplied by the probability of E1. So we know. So it's the same thing that comes here first before the next one is the, in this case, unsuccessful one. So we're going to write that same thing for that. So I'll write this same thing. I'll change the color a little bit so that you are not too confused. So this will be divided by probability of D given S multiplied by the probability of S. The same thing as the numerator. But I need to add the next one because this was for successful. So for the unsuccessful, it's going to be the probability of D giving U multiplied by the of U. That's the unsuccessful one. Somebody stop. All right. So this will be added to probability of detail giving U unsuccessful multiplied by the probability of U unsuccessful. Well, that is going to be the denominator. Write it down. And now we are ready to substitute. We are ready to substitute. Let me take you to the actual solution. Everything I'm doing is here. Okay. So this is redefining the terms as we did, handling the conditional probability, and then applying the theorem. This is what we have now. Okay. So now we are going to substitute this value. And what was the probability of D given S? If you can remember, the probability of D given S was 0.6. That's the probability of detail given. Oh, somebody even raised a hand, which means the person was ready. Okay, so that's going to be 0.6. I like the way, some of you are really, really ready. So this one here is going to be 0.6. What about this one? The probability of S is what? You can remember. What was the probability, Anastasia?
0.4.
It is 0.4. So you put in here 0.4. Now that you know what you're doing, it's not easy. And that will be the same thing down here, Abby. 0.6 and then times 0.4 again. Nothing changed. What was the probability of D giving you? D giving you, Anastasia?
0.2.
0.2. And what was the probability of unsuccessful?
0.6.
Very good. So now you can multiply and find the answer. If you do that very well and find the answer, you're going to get something. I mean, this one is calculated, 0.667. That's what you're going to get. What does this mean? So again, this is a revised probability from the original. We just rewritten them and eventually gotten this whole. So the probability of having a successful striking, given that you've done a detailed test, is going to be 66%. But that makes sense, right? So the chances, if you look at it, that 66% is approximately 70%. That is good news because it means that if you do detailed testing, your chances of getting a wonderful, successful well is very high, approximately 66.7%. Unlike the others, some of which were 0.6, 0.4, 0.6, 0.4, 0.2, this one, you have a huge, huge result. Fantastic, fantastic. So go through this latter part, and I'm telling you, by the time you eat your banku and you go through it, you would have understood this. Okay. So in summary, what have we done today? We have been able to define probability concepts, sample space, intersection, union. Hey, you remember union? Remember the additive rule? Remember mutually exclusive, non-mutually exclusive, joint event, conditional event, multiplicative, conditional probability. We did that. The additive rule, the multiplication rule. The most important thing for today is I'm bringing it all together, combining the conditional probability with the Bayes theorem. What didn't you understand the most? I know, it's a latter one, isn't it? It's a latter one. So what do? You go and look at it again, go through it again, and you will see in there the condition and why we use this particular theorem. Ladies and gentlemen, next time we meet, yes, I have Stella.
Sir, sir, please, can you help me explain the denominator for the equation that we just did?
This
I'm
one.
still trying to figure out, yes, how we got the P D given S and PS plus P given D, D given U, and PU.
Okay.
I don't know why
The
we have the two.
denominator here was because the events that were given to us, the conditional probability, so not the conditional, the base theorem. Let's go back to the base theorem. Appreciate it. So look at the base theorem. Okay. The base theorem says that the probability of A given B. But if we check very carefully in this very question, we have successful well and unsuccessful well, isn't it? Right?
Yes, sir.
But we also had detailed tests and not detailed test. And you can actually go and do a detailed test before you do successful welling. And you can also decide to do successful well before you go and do a detailed test to check whether the successful well that you have, whether the chances of you getting more oil is high. So in these two events, when you have two events, we indicated that you have to use this probability, the alternative probability here. And the reason why you got to use this alternative probability here, the last one here, in fact, is because the two depend on each other, not one directional, but two directional. Like, I depend on you, you depend on me. For example, when you give birth to a child, the father will say, this is my child. The mother will say, no, it's my child. The father will say, this is my child. But both of you dependent on each other. There was a condition that the father has to fulfill before the mother can get pregnant. And that condition, even if the father fulfills it, the mother has to get pregnant for the father's condition to mature. It's the same thing here. And so because of that, you needed the addition of the two events and their respective probabilities. You needed the addition of the two events and their respective probabilities. Maybe what I need to do again is to give you more examples away from this point. But remember that the Bayes theorem, this is a practical formula to use when you have two conditions where there are two events, when each one depends on the other, not that I depend on you alone. So you can use it in such a way where I depend on you alone. That one is looking more at the conditional probability. But Bayes theorem says that I depend on you and you also depend on me. And in that case, you don't use the upper formula, you use the down formula. That's it. So just go through it. You'll be able to get it. Now, Bayes theorem, you don't necessarily have to get it immediately. You have to pause and go through it step by step, sometimes with multiple examples. Next time, what we are going to do is this. What we are going to do is we are going to look at something known as probability distributions. Probability distributions. We're going to look at that. It's very easy, very common, very wonderful. Look at that. Then we can move on to the next one. Ladies and gentlemen, that brings us to the end of the entire